And I'm going to use that technique that we did last time of plotting out phasors, rotating phasors in the complex plane, to actually figure out what the solution of the differential equation is. There's a second way that I want to show you how to figure out the solution, which is relying on that wonderful little Euler equation, the e to the I omega t, that you can substitute in anytime you're going to use a sine or a cosine. I think what I will do is probably, I don't think we'll get to that today, I'll see how it goes, but what I'll probably do is shoot a video so that you can watch that alternate solution to this, especially if you're interested in that particular mathematical technique. On the final exam, the main things I am going to want you to know, cold though, about inductors, capacitors, and resistances are the physical analogies, are how to set up a differential equation, and are the fact that, well, when we take a look at these reactance numbers. So summarizing what we did last time, and I will finish that sentence that began with the fact that, but let me first call attention to this chart. We were saying last time, if I take any one of these three elements, a resistor, a capacitor, or an inductor, and I place a voltage across it. Now, this voltage does not necessarily mean the source voltage for the whole circuit. This would just be the amount, the function for the voltage across just that particular device. So far, we've been doing circuits where I did a circuit where the source voltage was the voltage across that device, because I was just applying the source directly to this thing. But once we've got a more complicated one, you could say each one of these three things might have a different time varying function for the voltage across it. However, if this is the voltage across just this element, then the current through the element, what we found last time, is always going to also be a sinusoidal function, a sine or a cosine, or I just put a cosine with an arbitrary phase shift. The current will have some amplitude if it's varying back and forth as a sine wave. Obviously, it hits some maximum current, it's some maximum negative current the other direction. And the amplitude for the current is going to follow this formula that looks a lot like Ohm's law, I equals V over R. The difference, and the reason why I'm calling this X thing the reactance of that circuit element rather than the resistance. And for today, I'll say we'll use the words reactance and impedance almost like synonyms. Again, in the video that I'll shoot for you with the e to the I omega t solution to this, I will actually push the idea that impedance is a complex number. And impedance is the term you use, not complex like complicated, but complex like it has a real part and an imaginary part. And impedance is the term you use if you're deciding that treating the problem in the complex plane is a useful way to handle these things. Reactance is always considered a real number, and that's actually the only difference between those two terms, is impedance gets the complex phase shift in there also. But for today, I'll just say those two words are synonymous. So what's the difference between that and resistance? Well, if I use Ohm's law and resistance, if I say current equals voltage over R, what I mean is the current at every instant in time is proportional to the voltage at that same instant in time. So in other words, if this was R, if this was a resistor, there should be no phase lag between these. If the voltage is going with cos omega t, the current should also go with cos omega t. And in my little chart here, I've said, yeah, for a resistor, reactance is just another name for the resistance, and there is no phase lag. So Ohm's law applies in its normal way. For these other two elements, a capacitor and an inductor, there is a phase lag. For a capacitor, the current is pi over 2, a quarter of a cycle, ahead of the voltage, which means the current leads the voltage by a quarter cycle. Or the way I usually like to think of it, the voltage lags the current. Why do I like to put it that way? Because I like to remember that capacitors live in the past. The voltage across the capacitor right now depends on what the current has already done, because the current needs to have already delivered charge to those plates. So the voltage right now across the capacitor should be lagging a quarter cycle behind the current. For inductors, on the other hand, voltage is L di dt, which means the voltage right now depends on the changes that the current is now making, depends on the current's plan for the future. So for an inductor, the voltage leads the current, or the current lags the voltage. So if I'm writing this equation for the current, it's a quarter cycle behind the voltage. Now the reactance for those two things, when I said, I want you to make sure you know for the exam the following facts, and then I went off and did a whole little side essay before finishing one of my facts, the reactance is the thing that I want you to know. In particular, I want you to know that for a capacitor, if I put a really high frequency signal through it, it's going to act as if it was a really high impedance or low impedance device. I put a really fast signal through a capacitor. So I run current back and forth through the capacitor really fast. Does it build up very much voltage across it?
No.
No, because there's no time. Every time it starts charging one plate, the current switches around and discharges that plate and charges the other one. So if I run even, a fairly high amplitude current back and forth through a capacitor, if I'm running it fast enough, the voltage never builds up to very high amounts. I could take this same equation here and I could say, oh yeah, this means, the amplitude of the voltage is equal to the reactance or the impedance times the amplitude of the current. And you could say for a capacitor, I could run a fairly high amplitude current through there, but if I'm doing it at really high frequencies, I will never build up very much voltage across the capacitor. So it's acting like a low impedance device. In the limit as the frequency goes to 0, the capacitor is acting like a short. Seems like a strange thing for a capacitor to act like, since the current, the charge carriers cannot actually pass through it. But if I'm, reversing the direction of that current rapidly enough, then essentially the voltage across the capacitor will stay pinned at 0 because I've given it no time to build up any voltage on either side of the thing. So at high enough frequencies, your capacitor acts like a short circuit, acts like a zero resistance wire. At low frequencies, on the other hand, there's lots of time for the capacitor to build up voltage. So even a fairly small current could end up building up a really high amplitude voltage wave on that capacitor. So at low frequencies, in the limit where omega goes to 0, the capacitor acts like an open circuit. Which makes sense. It's similar to what I asked you to kind of be very familiar with for the last exam, which was that if I apply a DC rather than an AC signal, and I leave all the switches in place for a very long time, then we said the capacitor would start to act like an open circuit. And this is kind of the same thing here. If I say, oh yeah, remember that problem we did last time where I said that you left a switch open for a year and left the switch closed for a year, and after that year had gone by, your capacitor was very nicely at equilibrium? Well, if I was gonna then tell you, you know what? We've got some new news on that circuit. It turns out that although I've left that switch in place for a year, my voltage source is actually oscillating. It's an AC voltage source with a period of 1 billion years. So I just hadn't noticed yet because I only left it in place for 1 year. Well, you're going to tell me, I don't really give a shit. That capacitor, for all practical purposes, is still at equilibrium and no current is flowing through it. So if you're going to run the capacitor with a voltage across it that's ultra low frequency, then essentially no current's flowing through it. Yeah, 1 billion years down the line, or 500 million years down the line, when the voltage has switched polarity, sometime over that 500 million years, I've got to run enough current to get the charge over to the other side of the capacitor plate, but that is going to be an intensely slow current. So for all practical purposes, in the low frequency limit, your capacitor is acting like an open switch or a break in the circuit. Okay, how about an inductor? You get the opposite behavior for an inductor. Because for an inductor, the voltage drop depends on how rapidly the current through it is changing. So if I look at my formula for impedance, this formula implies that, yeah, at low frequency, my inductor has almost 0 impedance. But at high frequency, my inductor has very high impedance. This time you'd say, yeah, if I've got that 1 billion year power source, which is oscillating the voltage back and forth once every 1 billion years, I'll be running a current through that inductor, but the current will be changing so slowly that I'm not building up any significant voltage drop across the inductor. So the inductor is acting like a short circuit. Remember, I'm treating this as an ideal inductor that has no resistance of its own. A real life inductor probably you treat as both an inductor and a resistor combined. But for an idealized inductor where the only way to get a voltage drop across it is to have the current change, if the current's changing slowly enough, the voltage drop across that inductor is essentially zero. So the inductor at low frequency acts like a short. It lets current flow through it and there's no voltage drop. The inductor at high frequency, on the other hand, even if I'm running a tiny bit, a nanoamp of current back and forth through it, if I'm switching that current back and forth rapidly enough, the di dt will still be a really big number, and I'll have to apply a really big voltage to that inductor to get that current to flow through it. So at high frequency, inductors act like a really high impedance device. So at infinitely high frequency, you'd say they act like an open circuit. Or in other words, I cannot run any current through that inductor without making the inductor go crazy because the current is changing so rapidly. So at high frequencies, that would ramp the current through the inductor down to zero, and it would act like an open switch. Yeah?
Does a capacitor, that's going back to capacitors, does a capacitor being exposed to a low frequency voltage current behave like a capacitor that's just being exposed to a direct current?
Yes, exactly. So when I say open circuit, you might say, hey, open circuit, does that mean there can be no voltage drop across it? Well, actually, it doesn't mean that. An open switch can have a voltage drop across it. Here's a wonderful circuit with an open switch. I'll just take a battery. I'll take, say, a single resistor, tie them together like this so that if the circuit's connected, I've just got a steady current through that resistor. And then I open the switch. Well, this node, if I just define this as my ground node, then this node by definition is 0 volts. If this is a 20-volt battery, then this node up here by definition is 20 volts. And since there's no current through the resistor, there's no voltage drop across the resistor. So this node up here is also at 0 volts. So an open switch can totally have a voltage drop across it. Open switch doesn't mean the voltage drop is 0, it just means the current is 0. So yes, a capacitor in a DC circuit. So if I now add a capacitor to that circuit, I could say, yes, if I've left this circuit in place for a very long time, that capacitor is acting like an open switch, which doesn't mean there's no voltage on it. There is, and that also means there's positive charge on this plate and negative charge on that plate, but it just means there's no current flowing. Everything's come to equilibrium. If instead of this battery, I replace this with an omega equals 1 nanohertz power supply, so 1 cycle per billion seconds, then I could still say at any given moment, this capacitor is probably at equilibrium with whatever the voltage level on this happens to be right now. And yes, over the course of a billion seconds, I will see that charge gradually move its way back to the other capacitor plate, but because it's moving so slowly, that's a tiny amount of current that'll be flowing.
Thank you.
Gladly. And yes, not wanting to belabor those points since we made them last time, but those are going to be the most important thing I want you to know about inductors and capacitors moving forward from here, especially for those of you who are taking Carlos's circuits class next semester. You'll have plenty of practice solving the differential equations and everything. But if I want to be able to look Carlos in the eye and say I'm proud of the what everybody who I'm sending to you knows, the main thing I want you to know about inductors and capacitors is going to be that limiting behavior and a little bit of the leading and lagging phase stuff that we're talking about. Solving the differential equations, you'll have plenty of time to get good at that next semester. Nonetheless, I would like us to finish up today able to set up, most importantly, and because the phasors give you an interesting geometric way to think through the solution, to come up with a solution for the differential equation for this particular circuit. So what have I done on this particular circuit? I've applied a AC sinusoidal source voltage, which is V source, the amplitude, times e to the I omega t. Or if you insist that today we're not using complex numbers, okay, fine, the real part of that is, not V naught, because I wanted to distinguish between the voltage across one of those devices and the voltage of the source. But the real part of this voltage is V source, cos omega t. And I've put all three of our friends, our three familiar circuit elements, in series together there. Now, this is going to act very much like a physical system that you're probably pretty familiar with. I think I'll actually put another sheet on the equation sheet for the final exam, which is nothing but a side-by-side electronic versus physical set of analogies. But help me out here. My voltage source, voltage in a circuit acts like what physical quantity in a physical oscillator? Okay, actually help me out then on the kinematics. Current in a circuit acts like what physical phenomenon?
Velocity.
Velocity.
Voltage is like a force.
Yeah, and voltage, like you said, is just like a force. Yeah, current acts like velocity.
Potential.
Charge, particularly the charge that built up on the capacitor plates, I think of as analogous to position. And when I say analogous, again, I'm not just saying they remind me of each other, but I'm saying you can set up exactly the same differential equations for both of these systems. And finally, di dt, the thing that's so important for an inductor,
Acceleration.
acts like acceleration, yeah. So, oh, and time acts like time.
That's amazing.
Isn't that deep? So, yeah, the voltage that I apply to the circuit acts like the force I apply to this oscillator. So if I've got an AC voltage, that's like I'm driving my oscillator with an outside alternating force, a force which is, pushed back and forth. How many of you then immediately in your mind said, oh, cool, that means we're going to be setting up like resonance situations?
Thinking more like springs.
Yeah.
Springs.
Okay, but springs are an example of resonance, or any system which is a mechanical oscillator, any system where if I give it some energy and then let it go. So the spring, I stretch the spring, putting in some spring potential energy, and I let it go. If the system's behavior would normally be to oscillate back and forth, then if I say, okay, let me complicate this a little bit. Instead of just giving it some energy all at once and letting it go, let me push it with an outside sinusoidal force, a time-varying force. Let me push it back and forth. In an alternate universe, I actually thought to hang that bowling ball from the ceiling right now. In fact, in an alternate universe, I hung it kind of at hand level, so I don't need to keep reaching down and breaking your line of sight in order to play with the imaginary bowling ball. So there's an imaginary bowling ball hanging here, and I'm kind of treating it like a cat toy. I push it that way, and I watch it oscillate back and forth, and I measure the frequency of that oscillation. And then I come back and I say, okay, now a more energetic cat starts, instead of just pushing it once, starts batting the bowling ball back and forth with this, time-varying outside source. So now the cat has, the bowling ball has a natural frequency that it likes to oscillate at. I could tell that with the first lazy cat who pushed the bowling ball and then just let it swing back and forth. However, my second cat has his own idea what the frequency should be. The cat's pushing it back and forth with the frequency that the cat makes up. That's called the driving frequency of this system. So now there's two frequencies, the natural frequency and the driving frequency. Remind me, under what circumstances might this bowling ball catastrophically start to damage its surroundings?
The driving frequency is the same as
If the driving frequency is the same as the natural frequency. That's what we mean by resonance. If the natural frequency is and the cat comes by and starts hitting the thing back and forth at a much higher driving frequency, the bowling ball will oscillate. In fact, it'll oscillate at the driving frequency, but it won't oscillate with a very high amplitude, because every time it starts going, the cat reverses and pushes it the other way. Then if a much more mellow cat comes in and starts pushing it back and forth with this really slow driving frequency, much slower than the natural frequency, again the bowling ball will oscillate, but it'll oscillate with a fairly low amplitude. But if the third cat comes in and the cat's driving frequency happens to match the bowling ball's natural frequency, then with each push from the cat, that's kind of in phase with the motion that the bowling ball was already doing, and its amplitude is going to build up higher and higher. That is the phenomenon that we call resonance. Resonance says you have to already have a system that wants to oscillate on its own, where if you just gave it some energy and then left it alone, it would oscillate. I'm not saying it would oscillate forever, it can be a damped oscillator, but it would oscillate. Then if you say, instead of giving it some energy and leaving it alone, I'm going to push on it with the sinusoidal driving force, then if the frequency of your driving force matches the natural frequency, then you will get a really high amplitude to the resulting oscillations. This can be something you want to happen. You can set up a system where you want it to resonate at a given frequency. Or this can be a disaster. If I build a building, and if Godzilla were to come up and treat the building like a Godzilla toy and push it sideways and then let it go, and you watch the building rock back and forth at a certain frequency, then at least if I'm building this thing in California, I'd better make sure that whatever that natural frequency is not likely to be the same as the frequency of what?
Godzilla's.
What's that?
Godzilla's? No, like an
Well,
earthquake.
okay, if Godzilla does show up, then I need to make sure that Godzilla agrees not to push the thing in resonance with its natural frequency. But I was thinking more along the lines of an earthquake, exactly. Whatever frequency the ground starts shaking back and forth in an earthquake, that will act like a driving force as far as the building's concerned. If that matched with the natural frequency of the building, then the building's oscillations are going to build up to higher and higher amplitude until it will probably fall over. In fact, this is one reason why sometimes, when you're looking at earthquake damage, you'll see, a street full of buildings that have withstood it pretty well, and then just one building that's in rubble in the middle of it. One possibility is just it wasn't built very well, just in terms of basic structural stability. But another possibility is that the frequency of those earthquake waves matched one of the natural frequencies of that building. By the way, the reason I say one of the natural frequencies is usually there's more than one way you could make a building oscillate. And, a different Godzilla could come up and twist the building and let it go. And you'd have a natural frequency for that torsion mode. You'd have a natural frequency for it spinning, oscillating on this axis. You might have a completely different natural frequency for it oscillating on this axis. So an architect who's working in seismically active zones has to be aware of all those different modes of oscillation that their building can undergo and make damn sure that they don't match the probable frequencies of earthquakes in that region. All right, so that's the phenomenon of resonance. If we're driving this circuit with an oscillating voltage, that's exactly the same thing as driving a physical system with an oscillating force, and we expect that same resonance phenomenon. Now, what are some other analogies we've said? An inductor acts like an object with mass, because voltage equals L di dt is essentially exactly the same equation as F equals M dV dt. A capacitor acts like a spring because the equation F equals Kx is the same equation as voltage equals Q over C. Except that our spring constant we usually put in the numerator of that equation. Our capacitance went in the denominator, so that means actually the capacitance C is analogous to 1 over the spring constant. A high capacitance means a very weak spring. A low capacitance means a very stiff spring, high spring constant. And finally, resistance is analogous to viscous friction. One way I sometimes write the equation for viscosity would be force, well I won't put the minus sign because that's just the direction of the force, but the strength of the force is some coefficient beta times the velocity. That is analogous to the voltage across a resistor being the current times the resistance. So the resistance is like that beta, that viscous constant for a viscous drag force. Okay, so my circuit that I've set up there is essentially the equivalent of setting up an oscillator that has a mass, a Hooke's law spring, and some viscous resistance to gradually damp the energy out of it, except that I'm going to be driving it with a sinusoidal driving force. Now, what will be the equation that I will get for that? Well, I could do Kirchhoff's loop rule. Again, I've told you before, I think Kirchhoff's loop rule is a little bit overrated in the sense that it is just kind of common sense, but I start at any point on the circuit, and I just navigate my way around a loop. If this was a more complicated circuit, I might say specifically, I'll navigate my way around this loop, and then maybe we'll come back later and do this other loop and get another equation. But in this case, there's only one loop that I can navigate around. So I'll start here, and as I navigate my way around this thing, each time I pass something where the voltage is going to change, I will keep track of those voltage rises and drops. So if I start navigating my way counterclockwise around that circuit, the first thing I pass is the power source, and I'm going from its canonically negative terminal to its canonically positive terminal. I know both of them are oscillating back and forth, but I'll just say that, I'll say that this equation refers to the voltage of that top terminal relative to the bottom one. So the first thing I do is my voltage goes up by an amount which is V source times cosine of omega t. What happens next? I hit that resistor. And if I'm saying this is my canonically positive voltage terminal, then I will also say this is my canonically positive direction for current. Again, what do I mean by canonically positive? I mean, depending on what moment in time I read this, the current may or may not be going that direction. But if I tell you, oh yeah, this moment the current's positive 3 milliamps, I mean that it is going that direction. If it's going the other way, I'll say it's negative 3 milliamps. So, does my voltage rise or drop when I cross the resistor? Well, if the current's going in that canonically positive direction, what does the voltage do when I cross the resistor? Drops. So I'll do minus IR. If the current's going the other way, I'd say that's fine, because then I will be negative, so minus a negative will give me a voltage rise. Then I hit the capacitor. And again, I want my canonically positive direction for current to be compatible with my canonically positive plate on the capacitor, so that my current feeds the capacitor. So I'll say, yeah, now I should get minus Q over C. The voltage should drop as I cross that capacitor, if that positive plate is the one carrying positive charge. And finally, as I pass the inductor, if I is increasing in that positive direction, then I am going to need to apply a forward voltage drop across the inductor to drive the current to increase, or to push that increase of current through the inductor. So I'm going to get minus L di dt. And finally I got back where I started, so all those voltage drops add up to 0. So there's my differential equation. Now the only problem is I've got two different variables, current and voltage. Or current and charge on the capacitor. I could run this making any of those my main variable. Several times in the past when I realized, oh yeah, I've got the charge on the capacitor and I've also got the current through the capacitor as a different variable, I've ended up saying, well, why don't we just say that the charge is a stand-in for the voltage, Q over C, I can just write as voltage across the capacitor. And then we said the current I could write as CdV dt. We gave an argument for that many times, which means di dt would be the second derivative of voltage. Since I also say, hey, we could pick either one of those variables as our main one, why don't this time I'll pick Q as the main one? Partly by analogy with the fact that if I were doing the physical oscillator, I would probably write it in terms of position as my main variable rather than velocity. So if I decide that Q is my main variable, I'm going to do two things with this differential equation. I'm going to move all those negative terms to the right-hand side so that I don't have to keep remembering the minus sign. And I'll say, so one of them is 1 over C times the charge. The next one is R times the current. How's the current related to the charge on the capacitor? Well, again, this is why we wanted to make sure that our sign conventions were consistent. If I've got a current running down this branch, that current is delivering charge to this positive plate of the capacitor. So the charge on the capacitor is increasing. How rapidly is it increasing? The current is just another name for dq dt. And finally, that means di dt is just another name for d squared q dt squared. Now, in another universe where we were literally setting up a sinusoidal cat who is messing with a mass that's on a Hooke's law spring attached to the wall, then we would say the acceleration of the spring should be the total force acting on that spring divided by the mass, or I'll put the mass on that side. And what is the total force acting on that spring? Well, we've got the minus kx from the spring. We have got minus beta dx dt from the viscous drag on that spring as it cuts through the air. And finally, we have got the force delivered by the cat, who's our outside driving force. And you notice, if I take that equation and I rearrange it, I get this. The cat force equals positive kx, I bring it over to this side, plus beta dx dt, plus md squared x dt squared. It's exactly the same equation we got here, just with the names of all of the parameters changed. So when I say there's analogies between a physical system and an electrical system, again, I don't just mean kind of poetic analogies. I mean, no, it is exactly the same dynamics. Yeah.
Why did you choose to put in those terms specifically?
To put what in which terms?
To substitute for those.
Well, I wanted to have only one variable that I'm keeping track of. So I wanted either Q or I, or sometimes I use the voltage across the capacitor, but I want to put all of these things that are changing dynamically in the circuit in terms of one function. So, you know, differential equation, you're not solving for a variable, you're solving for a function, but I want to have, since I've got one differential equation, I want to have one unknown function. So I decided Q of t was going to be my unknown function. Sometimes in the past when we've set these up, we've decided V capacitor is our unknown function, which is, yeah, along the same lines. All right, so we've got everything set up here. How am I going to actually solve this? Well, one thing I could do would be to just say, you know, I bet sometime in 4A you did a damped oscillator, and let me just kind of ask you to haul out your notes from 4A and see what solution you came up with. But other than remembering that it did have something to do with that resonance phenomenon, that might be a little bit rusty. Now, rather though than just propose an ansatz, what ansatz would I propose? Probably that the charge on the capacitor plate is gonna be sine or cosine of omega t, but that because there's some resistance, it's gonna gradually die out towards zero. So I might put a sine or a cosine multiplied by an exponential decay equation. Well, I might do that because, as it turns out, I've read the spoilers, it works. That is the solution to that equation. It is a sine or a cosine with a phase lag multiplied by an exponential decay, and by plugging that ansatz in, we can figure out both what the phase lag has to be and what the exponential decay constant has to be. However, rather than go through the algebra of doing that, like I said, I'll shoot a video where we do go through the algebra of doing that, only instead of mucking around with a cosine with a phase constant in it, I will take the liberty of doing everything in the complex plane and using e to the I omega t's, which are a lot cleaner. But what I'd like to show you today is one use we can get out of those phasors that we were talking about last week. So I'm going to say this. I am going to actually say kind of propose an ansatz. I'm going to say I do think that the current running back and forth through that circuit varies sinusoidally. In other words, it is a sine or a cosine. And that its frequency is the same as the driving frequency. So omega, I'll even call this omega naught, just to distinguish it from the natural frequency of the circuit, which could be something completely different. I'll say, okay, there's your driving frequency.
Are we talking about the current or the charge?
Both of them, actually, because if the the current's the derivative of the charge, or the charge is the integral of the current. If the charge is varying as cosine of omega t, so is the current. I get another 90-degree phase lag when I take the derivative of the cosine, and I get a factor of omega by the chain rule. But when I say the current is varying sinusoidally, if the charge is, then so is the current. I'm actually, for the phasor way of doing this, I'm gonna make the current be the main variable that I focus on. But once I've got one of them, I can always integrate the current to get the charge, differentiate the charge to get the current. So it's different ways of solving the same equation. What do I actually want to do here then? I want to set up my real and imaginary axes, and across both the voltage across any one of these three devices and the current through the circuit as a whole, if they're varying sinusoidally with time, that means I can write them as phasors. Remember, a phasor was something where I kind of draw a vector in the complex plane, and I say, if I just let that vector rotate counterclockwise at frequency omega, then over time, the vector will trace out this circle in the complex plane, and at any given moment, the real part of that number is the actual physical thing that I can measure. So if that phasor was supposed to represent current, then at any given moment, as the phasor rotates in its circle in the complex plane, the real part of its value tells me the current I'd actually measure in the circuit. If that same phasor was meant to represent a voltage across one of the devices, the real part represents the voltage that I could measure at that moment. Now, for all four devices, the source and all three of those other things there, they all share the same what? I put them all in series, so they all share the same current. They all share the same current. So rather than what you would normally think of as the right way to do cause and effect, saying the thing that's causing this whole phenomenon is the voltage at the source, and I want to figure out how it affects the voltage across each of those others or the current through each of those others. The problem is, if I'm focusing mainly on voltages, each of these four devices has a different pattern for its voltage. They're not even in phase with each other. Again, whatever the current is, the voltage across the resistor will be in phase with the current. Voltage across the capacitor will lag the current. Voltage across the inductor will lead the current. So if I'm thinking in terms of voltages, they're actually going to be kind of a pain in the ass. So what I'm going to do is I'm going to start from my ansatz. I'm going to say the one thing that all of those elements have in common is the same current function. I don't yet know its amplitude, but I'm going to just kind of start by drawing my current phasor, and I'm going to try to work backwards and figure out what all the voltages have to be. So I take my nice little complex plane thing here, and I say, okay, the first phasor I'm going to draw on it is a phasor for the current. So I am kind of trusting my ansatz and saying whatever the current ends up doing, it is going to be varying sinusoidally, which means I can represent it as a phasor here in the complex plane, and that green phasor is going to be rotating with frequency omega. Now, one way of thinking of Kirchhoff's rules is saying the combined voltage drop across these three elements equals the voltage from the source. So I'm going to try to draw in three voltage phasors, one for the voltage across each of these elements. I'm going to add them together, and I'm going to say they should add up to the source voltage phasor. And I'm going to draw them all starting from the current phasor that I've already postulated there. So if this green phasor represents the current through the entire circuit, how would I draw a phasor that represents the voltage drop across the resistor? Yeah, it would be in phase with the green one. So the voltage drop across the resistor would look something like this, drawn as a phasor. Now, that means that red phasor there, its length is the voltage drop across the resistor. Twice per cycle, the actual real value that I would measure for that voltage is going to be equal to this V sub R amplitude, there and there. Twice per cycle, the voltage I measure across the resistor will be 0, there and there, because the real part of that phasor would be 0, and the rest of the time it's somewhere in between. So that red vector, which is oscillating in phase with the green one, is the voltage across the resistor. I tried to fool you on this last time, so I won't insult your memory by trying to fool you again. But in an alternate universe where I was trying to fool you, If I tried to say that the voltage, that I drawn it so the voltage across the resistor is actually smaller than the current, you would scoff and you would say what?
They're apples and oranges.
You're comparing things with two different units. Yeah, I'm using a completely different scale for voltages than I am for currents. However, I could say, if I now draw the voltage across, let's say, the capacitor, if I draw the voltage across the capacitor as a smaller vector than that red one, I would be saying that I'm kind of, drawing it as if the voltage across the capacitor were smaller than the resistor voltage. Now, when I do draw the voltage across the capacitor, should it be leading or lagging the current?
Should be in phase with it.
Current leads voltage for capacitor, or voltage lags current. And again, that's my whole argument. The capacitors live in the past. The voltage right now depends on what the current has already done. So the voltage phasor for the capacitor is going to be a quarter cycle off, which means, it's actually lagging a quarter cycle behind on these complex plane circles that they're doing. What's it going to look like? I don't know. Let me draw it as if it was a pretty big voltage compared to that one. So, and I can say that this voltage is big compared to that one. I can't say it's big compared to the current, because those are two different units. But here could be my voltage across the capacitor. How did I calculate it? Why did I say the capacitor had a bigger voltage? Well, it might be that at whatever frequency we're at, when I compare, I haven't said how many ohms of resistance that is and how many farads of capacitance, but presumably if we were setting this circuit up in lab and analyzing it, we would start out already knowing what R was and knowing what C was. And for that matter, I know what omega I'm driving the thing with. So if it turns out that 1 over omega C, the impedance of that capacitor at this frequency, is smaller than R, then that means I'm going to get a bigger voltage drop across that capacitor. Now, again, I'm not saying that I've plugged in numbers, because I haven't, but that's how you would know how to compare them. You would actually measure the impedance of each of the three devices, and the devices with larger impedance. Oh, I'm sorry. The impedance across of the capacitor would have to be larger than the resistor, I'm sorry. The devices with larger impedance would get a bigger voltage drop for that same current. All right, so there's my voltage across the capacitor, and the way I have calculated its value is I took the impedance of the capacitor times the current. The way I calculated this value was I took the resistor times the current. And finally, I've got my inductor. Well, the inductor is going to be a quarter cycle ahead of the resistor. Voltage leads current for an inductor. So I'll draw this. And maybe the inductor has a somewhat smaller impedance than the resistor. So maybe that's what I get for my inductor. Phasor. Go ahead and put that label out here so we know which phasor it's talking about. Okay. Now, at any given moment in time, I get the total voltage across those three devices by adding up those three red phasors. Now, of course, what we're actually physically measuring in real life is the real projection of each of those. But with vectors, if I say, oh yeah, I've got 3 force vectors I want you to add up, and then I want you to take the x component of the final result. Which is the right way to do that? Do you first add up the 3 force vectors and then take the x component? Or do you first take each of the x components and then add them up?
X
First.
Whatever.
Do you have to?
No.
Okay, yeah, it shouldn't matter. Although if you were saying, but no, what I like to do is first I find all the x components and then I add them up. And that's how I get the x component of the whole thing. That's totally cool. But you could do it in any order. You could first add the vectors geometrically head to tail and then take the x component, or you could first take the x component of each one and then add them up. Same way with these phasors. If the actual physical voltage measured in the circuit is the real component of each of these phasors, I could either first project each one down onto the real axis and add up those 3 numbers and say that should be equal to the voltage from the source at this moment. Or I could first add up those 3 vectors head to tail and then take the real component. I'm gonna take that second thing. The fact that they're all at a right angle to each other means I think it'll be kind of easy to add them all up head to tail. In fact, when I add them up head to tail, the capacitor and the inductor phasors are gonna do what? Yeah, they're gonna subtract from each other. They're gonna partly cancel each other. If they were actually at exactly the same length, then they would actually cancel out to zero. But in this case, I've drawn it so that the inductor had a higher impedance than the capacitor, which meant it ended up with a longer voltage phasor. So when I add them up, the first thing I might do is say, all right, here's what I get if I take the voltage across the inductor and I add the voltage phasor for the capacitor. What do I end up getting? I get this combined red vector like that. And I can say, all right, this is voltage on the capacitor plus voltage on the inductor. And what's it equal to? It's equal to, well, the voltage across the capacitor is the impedance of the capacitor times the current, amplitude. And the voltage on the inductor is the impedance of the inductor times the current amplitude. And while I'm saying I'm adding the vectors, I actually subtract their amplitudes to get the amplitude of this one. Yes?
Is the bottom one an inductor or is it a capacitor?
What did I say? Oh, shit. Can't read my own handwriting. This one, I'm sorry, was the capacitor. This one was the inductor. And my L's look exactly like C's. However, the inductor should be leading the voltage. The voltage of the inductor should be leading the current. The voltage on the capacitor should be lagging the current. So yes, this is the right way. Which I guess means, well, yeah, I did put it this way, X capacitor minus X inductor. Or I can say that means I take the difference between those two impedances times I naught. That's what I get when I sum up those two vectors. Then what do I add it to? I add it to the phasor for the resistor, which was just IR. And what do I get when I add those two vectors? I mean, vectors in the complex plane, a real part and an imaginary part, act exactly the same way as two-dimensional vectors on an XY plane. I add those two complex numbers, I get this one. This is my overall voltage phasor for the three elements combined. But the combined voltage across those three devices has to add up to the voltage across what? The source. So this actually is equal to the phasor for the source voltage. Remember, I told you I was kind of doing the cause and effect backwards. In terms of cause and effect, you kind of think the source is what got this whole thing started, and now I'm trying to figure out how all the other things respond to it. But I kind of worked backwards. I said, I'm going to assume that we end up with some current phasor, and then I worked backwards until I figured out what the source phasor had to look like. Now, the current phasor at this moment would be in this direction, in phase with the resistor. So you notice, in this case, where we said the capacitor had more impedance than the inductor, the voltage of the source lags behind the current, or the current leads the voltage from the source. We call this a capacitive dominated circuit because the capacitor had the higher impedance. So capacitor dominated circuit, you get the voltage across the source doesn't lag a full quarter cycle behind the current like it would if there was only a capacitor in the circuit. But the voltage from the source does still lag behind the current, or the current does still lead the voltage. So a capacitive dominated circuit, a circuit where the capacitor has a higher impedance, acts a little bit like a capacitor and a little bit like a resistor. A resistor says the voltage should be in phase with the current. The capacitor says the voltage should be lagging a quarter cycle behind the current. The resistance and that capacitive impedance kind of come to a compromise and say, okay, the voltage will lag partly behind the current. How far does it lag? Well, I could find the phase lag actually by doing this. I could say this side of the triangle matched this little black vector I drew over here, this side of the triangle is capacitive minus inductive impedance times I naught. This side of the triangle is the resistance times I naught. So how big is that phase lag? Looks to me like the tangent of that phase lag would be the overall difference in impedance between the capacitor and the inductor divided by the resistor. So this would be actually, if we had done the differential equation out the long way, this would be what we ended up finding for that arbitrary phase lag that we put in there between the current and the voltage. How strong is that current? I started off just calling it I naught, but now that we know how it relates to V source, I could say, all right, it looks like this was R times I naught. This was kind of combined impedance of the capacitor and inductor times I naught. What's the overall length of this vector? What's the length of that V source vector? Pythagorean theorem tells me it looks like it's the square root of that black vector plus that black vector. So it's the square root of R squared I naught squared plus XC minus XL squared I naught squared. Or I can pull out the I naught and say V source is I naught. Looks a little bit like Ohm's law, except instead of resistance, I've got this thing that combines both resistance and the total effective canceled impedance of the capacitor and the inductor. So they sometimes call this the impedance of the circuit as a whole. And it depends both on the resistance and on the combined impedance of these two guys. Now, remember we started out saying, okay, V source was actually fixed. We decided that from the beginning when we hooked up that voltage supply. The circuit decided what I naught would be. So even though as we were doing the algebra, we kind of worked through it backwards. We started by drawing the I naught phasor and worked our way backwards to the relationship with V source. Physically, V source is the thing that happens at the beginning. So if I were to set up a, say, 30 volt AC power source, and then I were to vary the frequency. Now, as I change the frequency of that source, but I leave its overall amplitude at 30 volts, on this right-hand side of the equation, what's going to be changing under the radical sign? Is the resistance going to change?
No.
No. Is the impedance of the capacitor going to change?
Yes.
Yeah. As I raise the frequency, the impedance of the capacitor will go down. Is the impedance of the inductor going to change?
Yes.
Yes, as I raise the frequency, the impedance of the inductor will go up. What would be my scheme if I want to get the largest possible current? The only thing I'm allowed to change is the frequency of my source, which means resistance is out of my control. V source, the amplitude of the source, is out of my control. But XC and XL I can control. They both depend on that frequency. What would I try to do if I want to get the largest possible current amplitude? And I'm rewriting my final result here in this form.
Decrease the frequency.
Decrease the IC.
I could try to decrease IC down to 0, or I'm sorry, this was XC and XL. I could try to decrease XC down to 0. I could make the capacitor a zero impedance device by turning the frequency way the hell up. Do I want to do that?
No, because that doesn't allow current to go through the capacitor.
Yeah, if I ramp XC down to, well no, high frequency does allow current to go through the
Oh,
capacitor,
right.
but it doesn't allow current to go through what?
Inductor.
Yeah.
The inductor. If I try to ramp XC down to 0, I'm gonna be ramping XL up to infinity, and I'll actually get infinity under that square root sign. I'll get infinity in the denominator of this equation. Yeah, if I go to real high, so let me remind myself, the impedance of that capacitor is 1 over omega C. The impedance of that inductor is omega times L. Yeah, I could go to real high frequency, I could zero out this guy, but at the cost of making this one infinite. Or I could go to really low frequency and I could zero out the impedance of the inductor, but at the cost of making the impedance of the capacitor infinite. Now the capacitor wouldn't let any current through. What is my best solution? If I want the maximum possible current, and I fixed V naught, and I fixed R, for that matter, I fixed C and L.
Make them close to each other.
Yes, I want these two numbers to do what?
Go to 0.
I want them to cancel. I want them to go to 0. Yeah, I want XC to be equal to XL. So when will I get the maximum possible current through this circuit? It turns out if we've done everything correctly over there in our kind of little geometric walkthrough of the solution, it turns out I will get the maximum current when the impedance of the capacitor is equal to the impedance of the inductor. Then the impedance of the whole damn circuit will just be R. The resistor will be the only thing left that's contributing impedance. The capacitor and the inductor will have canceled each other out. Well, what do I have to do to make this happen? Impedance of the capacitor is 1 over omega C. Impedance of the inductor is omega L. I need to find a frequency where those two things are equal, so I solve this for omega. So I get omega squared, I multiply the omega up to that side, and I bring the L down to this side. So I get omega squared equals 1 over LC, or omega is 1 over root LC. Does that remind you of anything? Is that in any way a familiar result?
Yes.
That was the natural frequency of an LC circuit without a resistor in it.
Yeah.
If I was doing this as a mechanical system, I would say, hey, 1 over L, that's like 1 over M for a mechanical system. And C is like 1 over K, which means if I multiply those things together, I get the root of M over K, but it's in the denominator, so I flip it and I get the root of K over M. What's that?
That's the frequency.
Yeah, that's the natural frequency of a undamped mass spring oscillator. And we said if our cat, who looks like the cat diagram has made space for something else, but we said if our cat came along and started batting at that mass spring oscillator, what would be the condition where the cat would get the biggest amplitude from that mass spring oscillator? And we decided that would happen if the frequency of the cat's driving force matched the natural frequency of the oscillator. We're getting that same result here. What we just found is that resonance works the same way in circuits that it works for a mechanical oscillator. If I had just set a DC battery here and charged up the capacitor and then switched the battery out of the circuit, and I know on the exam, switching the battery in and out of the circuit turned out to be a whole little conceptual headache in itself. But if I flip a switch so the battery is no longer in the circuit and the charge can oscillate, yeah, the charge would oscillate through this thing at frequency 1 over omega C, and because there's a resistor, the current would gradually die its way down to 0. So that's like the cat first doing the test of saying, what if I just push on this thing and I let it go, and watching that natural frequency. Now we hook up the cat source here, and we say we're going to be applying this sinusoidally varying voltage. If I make the frequency of this thing equal to that natural frequency that the circuit would have oscillated at if I just charged it up and let it go, then I will get resonance. I will get the greatest possible amplitude for the current running through that circuit.
That's pretty cool.
I think it's pretty cool. This, by the way, is how a radio works. your radio antenna is picking up electromagnetic waves from the atmosphere, and it's applying those as a driving voltage to the circuit inside the radio. What's the circuit inside the radio? It's a regular old LRC circuit, actually with a very small resistance, so that resonance when you hit it will be very sharp. What ends up happening is your radio antenna is picking up simultaneously electromagnetic waves at a whole bunch of different frequencies, and it's applying them all as driving voltages to that circuit. Only your circuit is tuned so that 1 over omega c is whatever frequency you want to bring in. If you're trying to tune it to 106.7 megahertz, you set it so that 1 over root LC is 1.067 times 10 to the 8 cycles per second. Well, cycles per second, then you got to convert that into radians per second since we're doing omega, so another 2 pi in there somewhere. But how do you actually do this? On an old-fashioned analog radio, you would change the capacitance. In fact, we've seen some of the capacitors that you were playing with in class were taken out of an old-fashioned analog radio, and as you're turning it, you're just changing the area of the plates that are across from each other. But you tune that capacitance until your natural frequency is the same as the frequency of the station you want to bring in, and any waves from that station cause this circuit to go crazy and oscillate at high amplitudes. Any waves from all the other stations that the antenna is picking up cause the circuit to oscillate at very low amplitudes. So then when you feed the resulting oscillation to the speakers, the only thing you're actually going to hear over the speakers is the station that you were trying to tune in. So that's one example of resonance as a phenomenon that you want to happen. And of course, in electrical circuits, there's also many examples of resonance as something that destroys your circuit because you drove it at the wrong frequency by mistake. But in the same way as the Tacoma Narrow Bridge and disasters like that are examples of what happened when somebody drove a mechanical system at the wrong frequency by mistake. All right, that is mostly what I wanted to get through today. These are this result for the amplitude of the current through that circuit, and this result for the phase difference between the voltage and the current. These are the correct solutions to this differential equation that we were setting up. However, what I'm interested in the long run is not so much that you can make use of that exact solution. Those of you who take Carlos's class will have plenty of chance to practice that later. But that hopefully kind of thinking your way through this deepens your understanding of how these circuit elements actually behave. I will, again, shoot a video which is an alternate solution to this differential equation, sticking more to an algebraic method where we plug in our ansatz. The only thing that I think will make it especially interesting is I will go ahead and do the algebra using that Euler trick that instead of writing cosines and sines and phase differences, I can just do e to the I omega t's for everything, and we will see how that works out. Yes?
So will you be releasing questions soon for the final?
Yes. And videos on all those also. Our final is early in finals week for anybody who did not get that already. We have the first final on Monday morning. So I'm totally gratified that I get everybody's best, brightest effort right at the beginning of finals week. And if anybody's exhausted later on, it's some other professor's problem. But I also, though, recognize that we don't have I can't let you go 3.5 hours by default on this one, so I will definitely do my best to make this a one where time is not going to be the major factor.
Write like a 1 hour.
What's that?
Write like a 1 hour final.
I don't know if I can write a 1 hour final, but
That's what I mean. Try.
I'll accept 2 hours.
I think
try.
last time I was writing a 2 hour test and it didn't turn out to be
That's what I mean.
So
That's what I
I'll try
mean.
harder.
Write what you think is a 1 hour test.
And then
it'll take us 3 hours.
Yeah.
Monday.